Okay, we should be live. Just test the sound, talk to myself for a bit. See if we're using the correct microphone. Yeah, the microphone is fine. Okay, so go check out the website. We're developing BioniChaos.com. Go check it out. If you have any questions, there is a human in the loop. Just if you were wondering. And we forgot to start the LinkedIn stream as well. Let's start LinkedIn stream. It should come up anytime soon. Mule. Bear with me. Okay, it should be running up. Yeah, we have the stream on LinkedIn as well. Yes. Okay, that seemed to work. Okay, again, there is a human in the loop. If you have any questions, meant to be a human expert as well. So if you have any questions, fire away and I'll address them. I probably won't be able to answer them myself, so I'll engage one of the AI agents, one of the multiple AI agents we have access to. And now we'll do this EEG to music. So this tool was developed quite a while back. Is that volume okay? It's a bit weird, isn't it? Let's check the volume for a sec. Chromium volume is full. Okay. Can increase the volume from the tool itself. Yeah, so if there's a human asking a question, but I'm happy to explain the tool, in my own words. I spend quite a lot of time on it. But yeah, let the, notebook LM to talk about it real quick, 11 minutes. And then we will go from there.
Have you ever stopped to think about the uh, incredible electrical symphony happening inside your head right now?
It's pretty amazing, isn't it?
Yeah, I mean, we all sort of know our brains use electricity, but what if you could go beyond just seeing brain waves? What if you could actually, hear them?
That's a fascinating idea, and it's exactly what we're exploring today.
Oh, okay.
Yeah, this deep dive is all about a really innovative application called EEG to music.
EEG to music, right?
Exactly. It takes that complex electroencephalogram data, EEG for short, and transforms it not just into visuals, but crucially, into sounds, into music.
So like a shortcut to understanding what's going on in there.
You could think of it that way, yeah. A unique way to grasp the intricate dance of neural activity.
Okay, so our mission today is basically to unpack how this tool works.
Precisely. How it works, its key features, and what it can really tell us about EEG recordings, but using sound as a primary lens.
And we're drawing all this from the source materials specifically about this application.
That's right. Everything comes from the documentation and description of the EEG to music tool itself.
Great. So let's get right to the core idea then.
Okay.
At its heart, this tool takes raw EEG data, that electrical activity, and makes it something you can see and hear.
Yeah, that's the fundamental concept.
And this audible part, the hearing aspect, that feels really new, doesn't it? It adds a whole different way to explore brain activity.
It absolutely does. And how it does that is pretty clever. The tool processes 16 channels of EEG data simultaneously.
16 channels.
And to make sense of it all, it shows the data in two main ways: the time domain and the frequency domain.
Time and frequency. Can you break that down a bit?
Sure. Think of the time domain as listening to the raw moment-by-moment electrical chatter of the brain, like hearing every single note as it's played.
Okay, the direct stream.
Exactly. Then the frequency domain is more like looking at the musical score. It breaks down that activity into the underlying rhythms, the different brainwave frequencies.
Ah, so like how much delta, how much alpha, that kind of thing.
Precisely. It shows you the instruments playing, the different brainwave bands, and hearing it as music adds this whole sensory layer on top of the visual charts.
Got it. So how does a user actually start using this? How do you interact with the data and, well, hear it?
It's designed to be pretty intuitive, actually. The source material mentions a large scroll bar.
Like on a music player.
Yeah, exactly like that. You can just drag it through the EEG recording, and as you move it, you instantly hear how different sections sound.
Wow, so you can literally just scan through your brain's soundtrack.
Kind of, yeah. You can fast forward, rewind, find interesting parts just by listening.
And can you get more specific, like focus on certain things?
Oh, definitely. You can select specific channels. Maybe you only want to listen to the left hemisphere, for example.
Okay.
And you can define exact time windows you want to analyze. As you make these selections, the graphs update instantly.
Real-time feedback. Nice.
Yeah. And there are these features called auto volume and auto duration.
What do they do?
Well, they automatically adjust the loudness and the length of the sounds based on the EEG data itself. So stronger signals might sound louder or longer. It makes the listening experience more dynamic.
That sounds useful. Makes it more intuitive.
It does. Plus, you can apply filters. If you want to isolate, say, just the alpha waves, you can filter out the rest.
Okay, so you can really zoom in on specific brain activities, both visually and audibly.
Exactly. It gives you a lot of control.
This really feels like it could open up new ways to understand what's going on up there.
Mm.
Let's dig into some more of those powerful features.
Absolutely. Let's do that.
What really makes this tool stand out?
Well, the absolute core feature, of course, is the EEG to music conversion.
Right, the main event.
Yeah. And it's not just a gimmick. It directly maps those brainwave patterns into musical notes.
Why music, though? Why not just, I don't know, clicks or beeps?
That's a good question. Music taps into something more intuitive, I think. Visual data can be abstract, but changes in melody or rhythm, you can often feel them connect to a change in mental state.
Ah, so a calm, flowing sound might correspond to relaxation.
Exactly. Or maybe a more complex, faster rhythm when you're focused. It makes the abstract data feel more visceral.
I see. And you mentioned filters before, so you can shape what you hear.
Yes, that's where the customizable filters are key. You can apply things like wavelet denoise to clean up the signal, or bandpass filters.
Bandpass, that lets you isolate frequency ranges.
Precisely. So you can choose to only listen to the theta waves, for instance, which are often linked to creativity or drowsiness.
It's like having an equalizer for your brain's signals.
That's a great analogy, actually. It lets you tune into specific instruments in the brain's orchestra. You can really hear how different states, like deep sleep versus focused work, sound different.
That is powerful. You also mentioned selecting channels earlier. Does the tool clarify which part of the brain corresponds to which channel?
It does. The channel selector is crucial for that spatial understanding. There are 16 channels available, and the source specifies that channels 0 through 7 are generally from the left hemisphere EEG, while channels 8 to 15 are from the right hemisphere.
Ah, so you can compare left versus right brain activity audibly, maybe listen for differences during different tasks.
Exactly. You could explore how, say, solving a math problem sounds compared to listening to music, and how that differs between hemispheres.
Very cool. What about zooming in on the timeline?
Yep, that's the window size selector. It lets you adjust how much data you're viewing and hearing at once. You can go from a super detailed 1-second window up to a full minute, 60 seconds.
What's typical?
The default is 10 seconds, which is often a good starting point for getting a feel for the data.
Okay. And I saw notes about detrend and filter order. What are those?
Right. Detrend is usually on by default. It removes slow drifts, the DC component, using a wavelet method. Basically, it keeps the baseline stable so the signals don't drift off the chart, makes visualization cleaner.
Got it. And filter order.
That lets you adjust how sharp the bandpass filters are. You can choose from 1 to 4, with 2 being the default. A higher order means a steeper cutoff between frequencies.
So fine-tuning the filtering.
Exactly. Then there's also a whole spectrum toggle.
What does that do?
If you turn that on, it overlays the spectrum of the unfiltered signal, but specifically highlights the very low frequencies, below 0.5 hertz, and the higher ones above 30 hertz, alongside the standard filtered bands.
Giving you a broader frequency picture if you need it.
Precisely. And finally, a frequency scale selector lets you switch the frequency axis on the spectrum chart between linear and log scales.
Log scale can be useful for seeing details across wide frequency ranges, right?
Yes, it helps visualize lower frequency power more clearly, which is often quite high in EEG data.
Okay, that's a lot of control. So with all these features, what are the main things you actually see on the screen, the outputs?
Good question. You primarily get two key charts. First, the raw signal chart. That's in the time domain.
So the raw electrical ups and downs.
Yep. Unfiltered, just as recorded, shows you the immediate fluctuations over time.
Okay. And the second?
The second is the spectrum chart, which is in the frequency domain. This is where you see the breakdown of the filtered signals into those standard brainwave bands.
The delta, theta, alpha, beta.
Exactly. Delta, typically 0.5 to 4 hertz, associated with deep sleep.
Mm-hmm.
Theta, 4 to 8 hertz, often seen in drowsiness, meditation, or creative states.
Right.
Alpha, 8 to 13 hertz, that classic relaxed but awake state, maybe eyes closed.
The calm state.
Yeah. And beta, 13 to 30 hertz, which is prominent during active thinking, focus, alertness, problem solving.
So you can visually see which bands are most active and then hear the corresponding music.
That's the idea. You see the spectral power in each band, and you hear how that translates musically. And remember, if whole spectrum is on, you also get visual info on those frequencies outside the standard bands.
Okay, this is really where it clicks, isn't it?
Mhm.
Connecting the visuals, the sounds, and what they actually signify about brain states.
Absolutely. The real power, the profound understanding this tool offers, comes from making that abstract EEG data so immediate and, well, sensory through sound.
It moves beyond just graphs.
Yeah. It gives potentially invaluable insights into the underlying neural activity. You know, imagine a researcher trying to spot subtle changes or maybe an anomaly like a CG pattern.
They might hear it before they clearly see it in the complex waveform.
Potentially, yes. Or the sound signature might be very distinct and instantly recognizable once they learn it. It adds another layer to pattern recognition.
And who is this tool really for? Is it just for researchers?
Well, certainly researchers and students in neuroscience could find it incredibly useful, but the source suggests a broader audience too.
Yeah, cool.
Anyone who's just curious about their own mind, honestly. It makes exploring this data much more accessible than traditional analysis software.
That's a great point. And it uses real data.
Yes, the source mentions it utilizes intracranial EEG data from a project called NeuroVista, and that data is actually publicly available on eig.org.
So people could potentially download data and use this tool to explore it themselves.
That seems to be the implication, yes. It opens up exploration.
And is the tool still being developed? Are there future plans?
Oh, yes. The source outlines several future directions. They want to clarify how auto volume works and add a visual indicator for it.
So you can see the volume changing in real time.
Exactly. They're also exploring mapping rhythms more directly to EE bands, potentially converting the data output to JSON format for easier use elsewhere,
Makes sense.
improving the scroll bar's granularity for finer control, and maybe adding a channel summary overlay for quick reference.
Well, it's definitely an evolving project.
Absolutely. It shows they're actively thinking about how to make it even better, clearer, and more insightful.
Okay, so let's wrap this up. What's the big picture here? What does this all mean for, for us, for the listener?
Well, I think this deep dive shows how something as abstract as brainwaves can be made tangible, almost artistic through sound and interactive visuals.
It opens up new ways to explore and understand. It takes it out of the purely technical realm.
Precisely. It democratizes it a bit, perhaps.
And the idea of converting our own thoughts, our experiences as reflected in brain activity into music, that's pretty profound.
It really is. It raises some big questions, doesn't it? If our minds have a unique soundtrack, what could really listening to it tell us about consciousness?
Could we learn to interpret our own mental melodies?
Maybe even learn to influence them, compose our mental states. It's speculative, of course, but intriguing.
Yeah. And consider this. Maybe these sound representations aren't just for analysis. Could they become a new form of self-expression?
Or art. Imagine generative art based on real-time brain activity soundscapes.
Or even a way to understand neurodiversity differently through the different music people's brains make.
That's a fascinating thought. What hidden rhythms, what unique melodies might your own brain be playing right now?
Makes you wonder, doesn't it? It's a whole new way to think about listening to yourself.
Okay, so there is a human in the loop, just in case you were wondering. It's not just robots. Well, it's mainly robots, but there is a human expert as well. If you have any questions, go for it. We actually can have a robot telling you that as well, if you like. Where is it?
Everything.
Yeah, this one's voice is a bit funny, but it's probably better than what I'll be saying.
We do is available freely on Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Yeah, we have now a version of it.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
That's probably the better one.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
They are pronouncing the website name correctly, which is a good surprise. So go check out the site, let us know what you think. And we have a bunch of things that I actually don't remember if I played the audio for in the past or not. Someone was actually asking a question about converting brain signals to speech, whatever decoding speech. So we can do an overview of that. The G to music converter currently, I think it's a Flask application from memory. Let's actually check it out to confirm real quick. Because if it is, we'll have to redo it at some stage. Yeah, it is. We will, yeah, we'll like to redo it. We'll probably keep this one there as well. Could add this audio overview to the page. Yeah, these audio files, well, yeah, the good thing about them is that I can host them myself, but then on the other hand, they do get rather large very quickly. I mean, they each about 40-50 megabytes, but once you have, yeah, hundreds of those, then you can imagine what happens. You can imagine what happens. Yeah, we have some games as well that we are doing. The games are actually good because you can test the language. You can test how good the language models are. So we have these two versions of musical drawing. So you can select your instrument type, AM synthesizer, FM synthesizer. It's actually not doing much. You can do multi-touch on the touchscreen. I actually tried it. Yeah, this was developed by Gemini. Yeah, I'm not sure if we doing a standalone video of it. This will be probably going to the bottom of the page, but it's just interesting to see how these things work. We have another one. This one will actually it's kind of less interactive. You can do your drawing to begin with, and then when to play there's some bug. So this is what a neuron, a spike, will sound like. If you want to listen to a neuron spiking, you can use something like this. Yeah, probably that if you have like a second line, it's still just choosing the first one. Anyway, but you can see how Gemini is essentially understanding your prompts. So you can tell straight away kinda how good or bad the language model writing the code is, which is kinda important, especially for the way we do things. Okay, if there's no humans asking questions, we might jump back to Notebook LM.
Imagine for a second there's this hidden world all around us, full of invisible signals, stuff that defines, well, everything from our own bodies, our heartbeats, our brain waves, to how our phones and computers talk to each other. They're everywhere, shaping things constantly, but we hardly ever get to actually see them or hear them. So today, that's our mission in this deep dive. We want to unlock that hidden world. We're going to unpack the power of spectrograms, and we'll be using this really cool interactive online tool that honestly makes these complex signals feel intuitive, visible, and actually kind of fun to play with.
Yeah, absolutely. And a spectrogram, at its core, it's essentially that visual map you mentioned. It shows a signal's frequency content, what pitches are in it and how that changes over time. The real power, I think, isn't just seeing the shape of a signal. It's about understanding what it's truly made of, those different frequency components, and crucially, how they shift and evolve moment to moment. And what's great about this tool is it lets you explore all sorts of signals, from, simple generated waves right up to really important biomedical ones, the kind that tell the story of what's happening inside your body.
Okay, right. Let's unpack that then.
Right.
If we're mapping these invisible signals, how does a spectrogram actually do that? What are we really looking at on the screen?
Okay, think of it maybe like a musical score, but way more versatile for any kind of signal. So horizontally, that's your x-axis. That represents time. It just flows from left to right, and it corresponds to a specific time window you set in the tool.
That time window.
Yeah, and that window isn't just like a duration. It's the specific slice of the signal you're analyzing at any given instant.
So does the length of that time window change what you see? Could a really short window hide details, or a long one maybe blur things together?
That's a really insightful question. It absolutely matters. A shorter window gives you fantastic time resolution. You can pinpoint exactly when a little blip or change happens, but you might lose some detail on which specific frequencies are present. It's a bit fuzzier on the frequency side.
Oh, okay.
Conversely, if you use a longer window, you get much better frequency resolution. You can see the exact pitches, the exact frequencies much more clearly. But then you lose some of that precise timing. You know what frequencies were there, but maybe not exactly when they started or stopped within that longer window.
So it's a trade-off then. You choose what you want to focus on, time or frequency detail.
Exactly. It's a fundamental trade-off in signal processing, and the tool lets you play with that directly.
Cool. Okay, so that's the timeline, the x-axis. What about the vertical axis, the y-axis?
Right, the y-axis. That represents frequency, and it's measured in hertz, or hertz. Lower frequencies are down at the bottom, higher frequencies go up towards the top, and this goes up to whatever max frequency you decide to set, depending on the signal you're looking at. A really useful feature here, especially for certain signals, is switching between a linear scale and a logarithmic scale.
Logarithmic. Why would you use that?
Well, think about audio or even some biomedical signals like brainwaves. The range of frequencies can be huge, right? From very low frequencies like deep sleep brainwaves to much higher ones. A logarithmic scale kind of compresses that huge range. It lets you see detail in the low frequencies and the high frequencies clearly on the same graph, rather than having all the low frequency stuff squished at the very bottom on a linear scale.
I see. So it makes it easier to see everything that's going on across a wide range.
Precisely. Especially useful for audio perception and many biological signals.
Okay, and then there are the colors. They seem really important, painting this.
They absolutely are. The color you see at any point on that grid tells you the intensity, or you could say the power of the signal, specifically at that exact frequency and that exact moment in time.
Right.
The tool gives you different color map options, things like Viridis, which is common in science, or Inferno, Plasma, even just grayscale. But the principle is the same. Brighter colors, or sometimes hotter colors depending on the map, mean that frequency component is stronger, more dominant, louder, if you will, right at that point.
So it's like a heat map of the signal's energy changing over time and across frequencies.
That's a perfect way to put it, a heat map of energy.
And this is where that interactive part you mentioned really comes alive, isn't it?
Yeah.
Being able to tweak the signal parameters, change the display settings like the color map or the time window, and experience the sonification, the audio part.
Yeah.
It feels less like just looking at data and more like, I don't know, getting your hands dirty in a virtual lab. It must really help build intuition. But tell me more about the sonification. Why is hearing it so important when you can already see it so clearly?
Oh, the sonification is, it's often a game changer because it taps into a completely different way your brain processes information. Our ears are incredibly good at picking up subtle changes, patterns, and textures in sound. So visually, you might see a band of color get a bit brighter. But when you hear it, you might instantly recognize a shift in pitch, or a change in timbre, or maybe a little click or pop that corresponds to a tiny visual detail you might have otherwise overlooked.
So it adds another layer of understanding almost.
Exactly. Sometimes an anomaly or a feature just jumps out at you through the sound in a way it doesn't visually. It really deepens the connection to what the signal is actually doing.
Okay, that makes a lot of sense.
Yeah.
So we've got this powerful way to visualize and hear signals. What kind of signals can we actually explore with this tool? You mentioned a range.
Yeah, it covers a good spectrum. It starts with some foundational synthetically generated signals. These are like the basic building blocks.
Okay.
You've got the classic sine wave, just a single pure frequency. Doesn't change. It's the simplest waveform there is, really.
The fundamental note, sort of.
Pretty much. Understanding how these pure tones combine is, well, it's key to understanding more complex sounds and signals, like learning musical notes before reading a whole symphony.
Right. Makes sense. What else in the synthetic category?
Then there's the chirp signal. This one's interesting because its frequency isn't constant. It sweeps, usually from low to high or high to low, over time.
Ah, I think I know that sound.
Yeah.
Like a sci-fi pew sound sometimes.
Sort of, yeah. They're used all over the place, radar, sonar, because that changing frequency is great for measuring distance and speed. Also used a lot in testing audio systems to see how they respond across the whole frequency range.
Okay.
Then you have a pulse train. Think of it as just a series of regular on-off clicks or pulses. Super fundamental for digital communications. It's basically how we represent streams of ones and zeros, binary data.
The heartbeat of digital information.
In a way, yes. And finally, among the synthetics, there's white noise. This is basically random signal energy spread equally across all frequencies.
Like static on an old TV or radio.
Exactly like that. It sounds like shh. It might seem boring, but it's incredibly useful for modeling background noise in systems or for testing how robust a signal processing algorithm is. Does it pick out a real signal from the noise?
So even randomness has its uses. Have you ever used white noise analysis and found something like totally unexpected?
Oh, definitely. I remember one time working on an audio processing system. We were feeding it what we thought was a clean signal plus some white noise for testing. But the spectrogram of just the noise unexpectedly showed this faint but very distinct line at a specific high frequency.
Huh.
It turned out to be interference from some other equipment in the lab we hadn't accounted for. The white noise test, ironically, helped us find non-random interference we wouldn't have spotted otherwise. It made the unwanted pattern stand out.
Wow, that's a great example. Okay, so those are the synthetic foundational signals, but you mentioned we can also look at signals from, like, inside us, the biomedical signals. That sounds fascinating.
It really is. This is where you see direct, real-world applications, things happening in our own bodies. So first up, there's EEG, that's electroencephalogram. It measures the electrical activity of the brain.
Brainwaves.
Exactly, brainwaves. And what's so cool is you can generate signals that look like the different known brainwave patterns. You can see the slower delta waves associated with deep sleep, or theta waves linked to drowsiness or deep meditation. Then there are the slightly faster alpha waves, which you typically see when someone is relaxed, maybe with their eyes closed but awake. And then the faster beta waves, which dominate when you're alert, focused, actively thinking, or problem solving.
So you could literally, like, see the difference between chilling out and concentrating hard just by looking at the dominant frequencies.
You absolutely could. This tool lets you simulate those shifts, making those abstract mental states visually concrete. It's pretty amazing.
Yeah, that is amazing. What else?
Then there's ECG, or electrocardiogram. This records the electrical rhythm of the heart.
The heartbeat signal we see in hospitals.
That's the one. You can clearly see the characteristic parts of the waveform. The P wave, the big spike, which is the QRS complex, and then the T wave. Each corresponds to a specific part of the heart's contraction and relaxation cycle. But it's not just about seeing the normal heartbeat. Imagine seeing what, say, an arrhythmia, an irregular heartbeat, looks like. Something that might feel like just a slight flutter, or maybe nothing at all, could show up as a really obvious disruption in the pattern on the spectrogram. It highlights potential issues visually.
So it could be like an early warning system, visually speaking.
In a sense, yes. The patterns tell a story. We also have EMG, electromyogram. This picks up the electrical signals generated by muscle activity.
Like when you flex your bicep.
Exactly. You'd see on the spectrogram that as the muscle contracts harder, the signal gets both larger in amplitude, more intense color, and generally shifts towards higher frequencies. It gives you a direct look at how much a muscle is working, or potentially fatiguing.
Okay.
Then there's EOG, electrokilogram. This measures the electrical potential changes caused by eye movements.
Moving your eyes creates an electrical signal.
It does. It's subtle, but measurable. This is super useful in sleep studies. Those rapid eye movements during REM sleep. EOG helps researchers pinpoint exactly when REM stages are happening, which is crucial for understanding sleep quality and structure.
Fascinating. And one more, the PPG.
Right, PPG, photoplethysmogram. This one might be the most familiar to people now, even if they don't know the name. It measures changes in blood volume in the tiny blood vessels, usually in your finger or wrist.
Oh, like on a smartwatch or those finger clip things.
Exactly. That's the core technology. Your smartwatch shines a light, measures how much light is absorbed or reflected, which changes as blood pulses through. The spectrogram would show this rhythmic change in blood volume. The device then analyzes that rhythm to calculate your heart rate. So you're not just getting a number. The PPG signal itself, visualized, shows the actual ebb and flow of blood with each heartbeat. It's the pulse of life right there.
Wow. Seeing it laid out like that, it really makes you appreciate how much information these signals carry. This tool seems incredibly valuable then, not just for engineers, but for students, educators. Anyone curious about this stuff?
I agree. It really bridges the gap between abstract theory in textbooks and, tangible, visible phenomena, whether you're in signal processing, biomedical fields, communications, even audio analysis. It makes these concepts much more accessible and, frankly, engaging.
And it sounds like it's still evolving. You mentioned some future directions, like signal mixing.
Yeah, the developers have some exciting plans. Signal mixing is one. The idea is to let you additively combine different signals. So you could say, take a sine wave, add some white noise to it, maybe throw in a simulated ECG signal and see what the combined spectrogram looks like. You'd be able to observe things like constructive and destructive interference directly.
That sounds like you could create some really complex scenarios, like a virtual signal playground.
Pretty much. Another big one is real-time microphone input. Imagine being able to just talk or sing or play an instrument and see the spectrogram of that sound appear instantly on the screen.
Oh, that would be cool. Instant vocal analysis.
Yeah, or analyzing environmental sounds. They're also looking at adding advanced STFT controls. STFT stands for short-time Fourier transform, which is the mathematical process underlying the spectrogram. Exposing controls like the FFT size, the amount of overlap between those time windows we talked about, different windowing functions like Hahn or Hamming, these give you finer control over that time-frequency trade-off.
So more knobs to turn for the experts to really fine-tune the analysis.
Exactly. It's like having different kinds of lenses for your signal microscope. You can choose the best one for revealing the specific details you're interested in. And finally, they're planning data export options. So you could save the spectrogram as a high-quality image file, like a PNG, or export the raw signal data itself as a CSV file, or maybe a WAV audio file, so you can analyze it further in other software.
That makes it even more powerful for research or projects. So, okay, bringing this all together for you, our listener, what's the big takeaway? Exploring these signals, playing with these controls. It sounds like it gives you a fundamentally deeper grasp of how signals work, how they're built, how we analyze them, and maybe most importantly, how they underpin so much of the technology and even the biology that shapes our world every day. It's almost like getting, data X-ray vision.
That's a nice way to put it. Yeah, to sum up, a spectrogram isn't just some static graph. It's really a dynamic window, a window into this hidden world of rhythms, frequencies, fluctuations, everything from the mathematical purity of a sine wave to the incredibly complex electrical symphony happening inside our own heads and hearts. It makes the invisible visible. And I think what's really captivating is how this relatively simple visual representation can unlock such profound insights into really complex systems. It turns abstract data into something you can actually intuitively understand.
That idea of a window is powerful. Can you maybe share one more quick, surprising thing that window might reveal, something people might not expect?
Okay, well, sometimes in audio, particularly with machinery noise maybe, what sounds to your ear like just a single, steady, annoying hum, when you look at its spectrogram, you might discover it's not one frequency at all. It could actually be, say, 2 or 3 distinct separate frequencies that are very close together, and they're interacting, maybe beating against each other, which creates the perception of that single hum.
So what you hear isn't always the full picture of what's really there.
Exactly. And knowing that changes how you'd approach trying to cancel that noise, for example. You need to tackle the individual components. The spectrogram reveals that underlying complexity.
That's a perfect final illustration. So as you go about your day, maybe think about this. How could understanding these basic signal concepts, the kind of spectrogram lets you explore, change how you look at the world? Think about the charts and data visualizations you see constantly in the news and science articles, maybe even from your own fitness tracker or health app. Could understanding frequency and time give you a new lens to interpret that information more critically? What hidden patterns or stories are waiting in the data all around us if only we knew how to look? Lots to think about there.
Yeah, there is a human in the loop. Just in case you have any questions, there's a human expert, so-called expert. Don't trust anyone, of course. Check everything yourself. We need a bunch of disclaimers and things, don't we? And we have the bots potentially telling you the same thing, just in case you're more compliant when robots telling you what to do.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
So there you go. They actually sound less robotic than I was just watching the Neuralink presentation. I think it was posted a couple of days ago, yesterday or something. Yet these people are talking more like robots. I mean, there is a huge amount of money involved, so they have to repeat how great it is, how patients are happy, so on and so forth. Not actually mentioning any of the risks involved. I don't think they're showing any data, so on and so forth. So yeah, so sometimes robots are actually behaving in a more humane fashion than not. Okay, one thing we are missing is I actually don't always remember which tool we already covered, which can be a bit of a problem because we don't want to repeat ourselves. So let's see what's going on. So we covered the music. I mean, we made this one quite a while ago. This is still like a Flask application. We're actually trying to avoid Flask applications, trying to do everything in JavaScript, which, if we do everything correctly, should be more than doable, because we don't need any complicated libraries and things. Yes, if we're training something, we do it differently. We do it locally or on GitHub Collab. GitHub Collab? Yeah, GitHub Collab or Google Collab, whatever, doesn't matter. I think it's kind of the same. Well, it's not the same, but you know what I mean. Yeah, don't come after me. I don't actually use these tools much. Unless you have any questions, we might go music, FX, DJ, generate, do like reggae, cello, punk song, electro swing. Okay, let's try that out. Feeling adventurous? Yeah, it's a bit out there, isn't it? Electro swing. Electro swing. Let me know if it's too loud for your liking. Let's try to include some melody in it or something. I'm not sure. Okay, I have actually a bunch of things we need to fix on the website. Actually, I have an idea of what we could add to it. Yeah, I like the switch. The switch was nice. Let's keep this one. multiplying for a bit. Okay, I should be having quite a few things that works. Brain-to-speech, current status and communication alternatives. Yeah, not sure about that one. A bit out there. Yeah, potentially have something on comparative analysis of deterministic and generative artificial intelligence models. Yeah. Hey, not sure about that one. This, oops, this drawing thing. Yeah, let me know what you think. Xylophone trap beat. Sounds interesting. What's hyperpop? Okay, so I have Gemini. Check for a sec. Sorry, I can't actually see my other screen, but yeah, if you want to see it, to let me know. It's actually cycling of what's currently on BioniChaos.com. I have certification of the spectrogram tool as well. So this one showing EEG signals. Just there's an automated. There's like a demo we're trying to include. Yeah, essentially on each page now, we're trying to have a demo mode that will essentially show you like a demo of how the tool works. Then we have the notebook LM discussion, like a podcast style thingy. And if possible, we also have sonification, so turning whatever the signals that you see on the screen into audio. But yeah, obviously, that one's not very musical, so I might turn it off for a sec. It's just a bit annoying. Okay, we have this AI types. Open a live server. Okay, didn't we do this one quite a while back? Not sure about this one. Yeah, that's what it looks like. Yeah, that's what Gemini does. Yeah, why did you include finance and stuff? Yeah, we're trying to focus on healthcare. This channel, it could be interesting, you know, comparing the tools. Yeah, it's essentially comparing how the difference between deterministic and the generative AI in the healthcare. That doesn't make sense. Okay, so that would be generative. Yeah, it's not quite clear that. Yeah, it's deterministic on the left, generative on the right. Should we do? And should we publish this? I don't know. What do you think? We could add more biomedical examples. Okay, now I remember what was going on with that. Brain to speech. BCI for speech. And like a 5-minute audio for it as well. Deep research. Clinical horizon for non-invasive speech. What neuroprosthesis? Non-invasive. Why is it neuroprosthesis? Why is it called prosthesis? What? Too much stuff going on, obviously. Well, that's why it's called chaos. So embrace Yeah, let's actually stop this for a sec. Yeah, that happens. We lost the DJ. We lost the DJ. I'm not dropping any frames. What are you talking about? Check your connection. Should be fine. I have to close that window. Close that window. It might wrap up. Because there is... If there's any human, there's a human in the loop. Obviously, they can hear. I don't know if you can hear. I could be a robot. I could be the new model. Am I the new model? Well, you wouldn't know, would you? Well, because even with the current models, you cannot tell if it's a human or not. And so, good luck. Wait a sec. We have stuffed up the deep research prompt. Deep research prompt. Okay, now I remember. I think I remember. Okay, yeah, we got that. Then we turn it into... So what are we talking about? Yeah, we had the question in the comments. Someone said, can you detect the words a person wants to say based on their brainwaves? Yeah, I would not read the rest, but it's kind of personal. Well, I mean, it's a public domain, but I just don't think it's relevant. So the thing about it, say you want to know what you're recording somebody's EEG. So say hypothetically, okay, let's actually bring an agent to talk to. Go from there. Can talk to Gemini in here? No, I cannot. Why is that? It's odd. Let's do AI Studio. Okay, so we have a question. Can you detect what a person wants to say based on their brainwaves?
That's a fascinating question. While brain-computer interfaces are making progress in interpreting brain signals, accurately detecting specific words solely from brainwaves is still a complex challenge. Researchers are exploring different methods, but it's not a perfect science yet.
Okay, so how would you go about it? So there's different person might be in a different state. So for example, a different, say, vegetative state. What difference the state would make on how would you go about it?
The person's state definitely affects the process. In different states, like a vegetative state, brain activity can be very different, making it much harder to interpret brainwaves and detect intended words. The approach would need to be tailored to the specific state, often involving more advanced techniques to understand the altered brain activity and potential communication pathways.
So what happens if, say, they can move a finger or move the eyelids or something?
If they can move a finger or their eyelids, those movements can potentially be used as a form of communication. This could involve setting up simple codes, where a specific movement corresponds to a letter, word, or a response, like yes or no. These physical cues can act as a way to translate their intentions or responses, often in conjunction with other communication methods.
Okay, so in that case, would you need to record the brainwave EEG in the first place?
Not necessarily. If the person can make voluntary movements, like moving a finger or blinking their eyelids, those movements can be directly used as a form of communication, without needing to record their brainwaves using EEG. The focus would be on interpreting those physical cues.
Okay, and what happens if they cannot move, blink, move a finger, nothing at all?
If they can't make any physical movements, then detecting their intentions becomes much more challenging. In those cases, researchers might explore using more advanced brain-computer interfaces that try to detect specific brainwave patterns associated with thoughts or intentions, even without any physical response. It's a complex area of research focused on finding ways to communicate when physical movement isn't possible.
So what method, what would you use then? What type of brain recordings?
When physical movement is impossible, methods like electroencephalography, EEG, or more advanced brain imaging techniques might be used. These technologies try to capture and interpret the electrical activity in the brain, looking for patterns that correspond to thoughts or intended communication. Sophisticated algorithms are then used to decode these brain signals, attempting to understand the person's intended messages.
So how would you fine-tune an algorithm like that for a specific individual?
Fine-tuning an algorithm for a specific individual involves calibrating the system to their unique brainwave patterns. This typically requires collecting data from the individual while they try to perform specific tasks or think about certain words. The algorithm then learns the specific brainwave signatures associated with those actions or thoughts. This personalized training helps improve the accuracy of the decoding process for each unique individual.
So would you use basic EEG or different types of EEG or more sophisticated or like more invasive? Would you need to do more invasive recordings or would you go for like an MRI or something else?
The choice of recording method depends on the level of detail needed and the invasiveness that's acceptable. Basic EEG uses electrodes on the scalp and is non-invasive, making it suitable for many cases. More specialized EEG techniques can provide more detailed information. In some cases, more invasive methods like implanted electrodes might be considered for more precise brain signal recording, but these are typically used in specific scenarios. Techniques like fMRI, which measure brain activity by detecting blood flow changes, can also be used to understand brain activity, though they aren't typically used for real-time communication due to their size and complexity.
I think we exhausted that conversation. Might start going in a loop now. But yeah. And so we went discussing it with Jim. That was Notebook LM, obviously. We have a deep research prompt investigating the clinical viability of real-time speech synthesis from non-invasive neural signals. Okay, so this one, yeah, we turned into a discussion as well. Okay, what do we have? Shall we create a web page around this? See how Gemini handles that. Export the report. So we did like a deep research report. I don't know how many pages. Let's actually read this summary. Unless there is a human asking a question, I might just use a robots to talk about it while we're generating a website around this.
Imagine, just for a moment, communicating without speaking in the usual way, especially when maybe you can't. Today, we're doing a deep dive into something pretty cutting edge. We're looking at biomedical data, artificial intelligence, and this really ambitious goal of translating brain activity directly into speech. Yeah, so we've got a stack of material here for you. There's an overview of some really innovative tools from a platform called Biomedical, and also a detailed look at where things actually stand with brain-to-speech tech, plus, what the practical alternatives are right now. Our mission really is to unpack what's genuinely possible here, to sort of separate the science fact from the science fiction, and also explore the real-world solutions people use for communication challenges, and maybe uncover a few surprising things along the way. Okay, so as we started digging into this cutting-edge stuff, our sources kept pointing us towards this platform, BioniChaos. It sounds like a really comprehensive toolkit almost for understanding the body through data, combining biomedical data, tech, and education.
That's a good way to put it. Yeah, it's aimed at researchers, educators, students.
Yeah.
And what's really striking is just how broad it is, but also how interactive. It goes from basic signal processing fundamentals all the way up to quite advanced AI applications.
Okay.
So for instance, they have a spectrogram generator. You can actually see how brainwave frequencies, or ECG signals, change over time. And things like a Fourier series visualization, which sounds complex, but it basically shows how complicated biological patterns can be, well, broken down into simpler waves. It makes it visual.
Right, making the invisible visible, kind of.
Exactly. Makes those complex ideas much more tangible.
And digging into their tools, what really jumped out at me was the stuff related to brain activity itself. They've got like an interactive brain EEG simulation, visualizing EEG signals using PCA and ICA analysis.
which are pretty powerful ways to filter out noise and isolate specific brain signals.
Yeah, separating the signal from the noise, literally. And then, get this, an advanced EEG signal simulator, where you can apparently tweak brain waves and even simulate artifacts, things that might mess up a reading.
Precisely. It allows for controlled experimentation and understanding. And they don't stop there. They're looking into AI that understands why. So causality in AI models like LLMs.
Okay, that's deep.
And even AI-powered EEG speech decoding. It really feels like, as you said, a playground for curious minds wanting to connect these fields.
So if we pull back a bit, what does this collection of tools sort of tell us about the bigger picture?
Well, it really highlights this increasing intersection, this convergence of engineering concepts and biological data. You see it in tools looking at the multimodal medical data landscape, how combining different health data gives richer insights. Or Seizure Zone, that interactive 3D brain map for understanding epilepsy. They're pushing how we interact with and understand complex biological signals. And there are other notable things too, like exploration of the centrode, that's a minimally invasive BCI, a brain-computer interface, and even NeuroGPT, which is exploring how to integrate large language models like GPT with EEG analysis. It's moving fast.
Okay, so with all these incredible tools for understanding brain signals, maybe even decoding some aspects, the really big question arises. How close does this actually get us to, translating those squiggly lines, those brainwaves, into actual understandable words?
Okay, and our sources address this directly. It's framed as a major goal, definitely in BCI research, brain-computer interface research, but, and this is really important, but the tech to translate brainwaves into ready-to-use fluent speech, that's currently still very much experimental. It's research-level stuff.
Okay, so not something you can just, order online yet.
Not at all.
Yeah.
And the main reason is the sheer complexity of the brain. I mean, think about speech. It's one of the most intricate motor activities we perform. It involves multiple brain regions coordinating perfectly, and the specific neural signals for each tiny sound, each phone. They're incredibly complex, incredibly subtle, and crucially, very individual. My brain signals for hello are different from yours.
And it's not just the brain's complexity, is it? It's also the equipment needed.
Exactly.
Our sources were pretty clear that the really groundbreaking research, the stuff getting closest to decoding speech intentions, it's not using those simple EEG headbands you might see advertised.
No, not typically. They're often using methods like electrocorticography or ECOG.
ECOG, that sounds serious.
It is. It's invasive. It means placing electrodes directly on the surface of the brain.
Wow.
Which usually only happens if someone is already undergoing neurosurgery for another reason, like epilepsy monitoring. The signal quality is much higher, much clearer, because you bypass the skull.
Okay, so that's a major limitation for general use.
A huge one. Or, alternatively, they might use high-density EEG, which is non-invasive, but we're talking hundreds of electrodes, fitted into special caps requiring conductive gel and needing expert technicians to set up and run. Again, not a simple consumer device.
Right, so a world away from just popping on a headset.
A world away. And it's important to distinguish this kind of specific speech decoding from maybe simpler BCIs people might have heard about.
Like the ED music thing you mentioned on BioniChaos. Or other projects turning brainwaves into sound.
Precisely. Those often work by mapping much broader brainwave activity, like the overall strength of alpha waves, associated with relaxation or beta waves, linked to active thinking to musical notes or parameters.
Okay.
It's like mapping your general mood to a chord, maybe. It's very, very different from decoding the incredibly specific, rapidly changing signals needed for language.
That makes sense. It's a difference in resolution, almost.
Absolutely. And another key factor our sources highlight is individual calibration. These advanced speech decoding systems aren't plug and play. They have to be trained meticulously for each individual person. This can take hours, sometimes days. The system learns your unique brain patterns when you intend to say specific words or sounds.
So it's highly personalized and requires significant setup.
Extremely personalized, yeah.
Okay, so given that direct brain-to-speech is still very much in the lab, highly complex, invasive, or requires specialized gear and needs tons of calibration, what about the here and now? What practical, effective communication methods are actually available for people who might need them, say, in a hospital setting?
That's a vital question, and the good news is there are established effective methods. Hospitals have specialists, like speech-language pathologists, who are trained to find the best fit. Often it starts simple, establishing reliable yes-no responses using any consistent voluntary movement the person can make.
Like blinking.
Exactly. Maybe one blink for yes, two for no. or squeezing a hand, moving a finger, wiggling a toe, whatever works reliably for that patient.
Low tech, but crucial.
Absolutely.
Yeah.
And then there are tools like letter boards or picture boards. The patient can use their eyes just looking at letters or pictures, or maybe point if they have some hand movement to spell out messages or indicate needs pain, thirst, needing repositioning. Simple, but incredibly powerful for restoring some communication.
Right. Restoring agency. And what about slightly more advanced options that are still widely used and non-invasive?
Yeah, the sources definitely point to eye tracking technology. This is becoming much more common and accessible.
How does that work exactly?
Basically, a camera tracks the patient's eye movements very precisely. Those movements are then used to control a cursor on a screen. So just by looking, they can select letters to type out messages, choose pre-programmed phrases, or even control environmental systems in some cases.
Wow. So they can type with their eyes.
Essentially, yes. It's a really important form of what's called augmentative and alternative communication, or AAC. It bypasses the need for physical speech or hand movements entirely.
That sounds incredibly enabling.
It really can be. But, at the end of the day, the best approach isn't just about the technology itself. It's about working closely with the whole medical team, the doctors, the nurses, and especially those speech-language pathologists.
Right.
They can assess the individual's specific abilities, needs, and preferences to figure out which method, or maybe combination of methods, will be the most effective and empowering for them. Finding the right fit is key.
So we've covered quite a bit of ground here. We've journeyed from these really sophisticated biomedical data tools like those on BioniChaos that help visualize complex signals, all the way to the very ambitious but still highly experimental world of trying to get computers to understand speech directly from the brain.
And we also made sure to touch on the really crucial practical communication tools that are available and making a difference for people right now.
Yeah, the things that work today.
Exactly. So thinking about all this, what really stands out to you? What's the thing that catches your attention in this whole field? Is it maybe the sheer ingenuity behind these interactive tools, how they make complex science more accessible? Or perhaps it's that powerful reminder that even as technology leaps forward at this incredible pace, sometimes the most profound connections still rely on these really thoughtful, human-centered approaches. Simple blinks, eye gaze boards.
That's a great point. It's that tension, isn't it, between the high-tech dream and the low-tech reality that works. And maybe thinking ahead, how might future developments, things like that minimally invasive stentrode BCI or maybe deeper integration of AI like NeuroGPT, how might those change the landscape for patient communication? Could they start to bridge that gap between today's practical solutions and that brain-to-speech dream?
That's the million-dollar question, isn't it? And as we pursue that, we also have to keep thinking about the other really important questions, too. Things like privacy, consent, even personal identity when technology gets this close to our thoughts.
Yeah.
Lots to consider.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.